Performance study of a system with optimal location of Statcom device using MPMJ algorithm under normal operating conditions. Abstract optimal power flow solution is the backbone of power system operation, power system future design, stability analysis, and power system future expansion. To solve this optimal power flow problem, there are many traditional and meta-heuristics algorithms in the literature. The regular optimal power flow has visible limitations. It takes much time to converge and fails to produce the optimal values within the operating limits. Due to these drawbacks, the researcher shifted to a meta-heuristic algorithm. In this paper mainly devoted to minimize the fuel cost of the generator, improve the voltage magnitude, reduce active power loss, and voltage stability index using the mentioned meta-heuristic algorithm. The feasibility and effectiveness of the proposed algorithm approach are investigated and exemplarily demonstrated on the IEEE 30-bus test system. The performance of the optimal power flow performed by allocating the proper place of the Statcom device using the Analytical Hierarchy Process, AHP. From the simulation result for the given objective, the meta-heuristic TLBO, JAYA, and MPMJ algorithm compared with and without Statcom. Besides, the comparison is made with similar studies in the literature. Based on the simulation result, the proposed MPMJ algorithm is the most powerful for the optimization algorithm for the defined objective and selected test system. Keywords: AHP, MPMJ, OPF, Statcom, FACS, meta-heuristic algorithm. Introduction. Optimal power flow, OPF, is part of an integrated power system delivery solution. OPF main goal is to optimize the selected objective feature, including fuel cost, voltage stability indices, active and reactive power loss, and optimum power system control variables change. Nevertheless, it must satisfy reactive power limits on equality and inequality constraints. 1. The OPF problem was and remains one of the most investigated problems in power systems. Earlier, as stated in 2, several classical, deterministic, optimization algorithms were successfully applied, such as interior point methods 3, 4, Newton's method 5, linear programming method 6, nonlinear programming and gradient method 7 are useful to solve optimal power flow. Besides, the conventional methods have strong limitations in convergence, and they cause complications in obtaining the overall optimal solutions. Due to the problems mentioned above, the research focus has already shifted to the meta-heuristic algorithm. The varieties of meta-heuristic algorithm that can solve optimal power flow complication, like particle swarm optimizations, PSO, 8, a novel hybrid BAT algorithm 9, artificial bee colony algorithm, ABC, 10, and fruit fly optimization 11. Analytical hierarchy process effectively supports decision-making concerning complex sustainability issues and can help to recognize and define a problem in detail. It is widely used to decompose a decision problem into its essential parts, which are then structured hierarchically. As a result, AHP delivers a ranking of options which facilitate the selection of a strategy. Option 12. In this paper, the allocation of Statcom FACS device is applied on the bus by using Analytical Hierarchy Process, AHP, which in turn compares 4 parameters, namely fuel cost of the generator, active power loss, sum of voltage magnitude on the bus and voltage stability index. We have to select 5 weakest buses using the voltage stability index. Then, based on these 4 parameters, we can determine the optimal bus using that AHP method. 2. Mathematical modeling of Statcom device. Active and reactive power flow determined by the phase angle difference between the sources and by the voltage magnitude difference, respectively. Hence, Statcom can control reactive power flow by changing the fundamental component of the converter voltage concerning the AC bus voltage, both phase and magnitude sensible. 12. In 13, the placement of Statcom FACS device based on the PQ bus having low voltage magnitude and the rate Statcom MVAR rating is between -100 and +100 MVAR. A mathematical model for the controller to the inclusion of load flow algorithm derived from the equivalent circuit diagram of Statcom in Figure 2. Load transmission line Basactot converter plus. The Statcom power flow equations are derived from first principles and assume the following voltage source representation. The Statcom voltage injection bound constraint is as follows: VRV. Where and are the Statcom's minimum and maximum voltage? Min VRV. Max VRV. The current expression in 3 is transformed into a power expression by the VSC and power injection into the bus as shown in equations 4 and 5, respectively. K. Where and are the Statcom voltage magnitude and angle, respectively. VRV. VR. Modeling of OPF. 3 mathematical formulations of optimal power flow problem. Mathematically, the OPF problem can be formulated as a nonlinearly constrained optimization problem can be expressed as follows. Where f is the objective functions to be minimized, u and v are the vectors of dependent and control variables, respectively. F, u, v, objective function, e, u, v, set of equality constraints, I, u, v, set of inequality constraints. Where ng, nt, and nc are the number of generators, the number of regulating transformers, and the number of var compensators, respectively. The set of state variables for the OPF problem formulation are Pg1, active power output at the slack bus, VL, voltage magnitude at PQ buses, load buses, QG, reactive power output of all generating units, SL, transmission line loading, or line flow. The following equations give the objective function. Cost minimization. Inequality constraints. The inequality constraints can be considered the minimum and maximum values of generators, transformer, shunt var compensation, security or transmission line MVA rating, and Statcom voltage magnitude, and angles. The voltage of each load bus must be restricted within its lower and upper operating limits. Line flow through each transmission line ought to be restricted by its capacity limits. For Analytical Hierarchy Process method. The Analytic Hierarchy Process, AHP, is widely used in multi-criteria decision-making tools for tackling multi-attribute decision-making problems in real situations. 14. It represents a powerful technique for solving complicated and unstructured issues that may have interactions and correlations among different objectives and goals. 14,15. The mathematical modeling of the AHP methods can be: calculate the maximal eigenvalue of the judgment matrix max, where represents the jth element in vector A, JA. The consistency index of a hierarchy ranking CI is defined as where the maximal eigenvalue of the judgment matrix is n, the dimension of the judgment matrix max. The stochastic consistency ratio is defined as where Ri is a set of given average stochastic consistency indices and Cr is the stochastic consistency ratio. For matrices with dimensions ranging from 1 to 9, respectively, the values of Ri have been displayed in 16,15. It is evident that for a matrix with a dimension of 1 or 2, it is not necessary to check the stochastic consistency ratio. Generally, the judgment matrix is satisfied, acceptable, if the stochastic consistency ratio, Cr 0.10. V. Overview of optimization algorithms. Teaching learning-based optimization. The TLBO algorithm is a teaching learning process motivated algorithm proposed by Rao et al. And Subsani based on the impact of a teacher on the output of learners in a class 17, 18. The algorithm describes 2 basic modes of learning. I. Teacher phase. 2. Learner phase. I. Teachers phase. A group of learners is considered as population and different subjects offered to the learners are considered as other design variables of the optimization problem, and a learner's result is analogous to the fitness value of the optimization problem. The best solution in the entire population is considered as the teacher. The design variables are the parameters involved in the objective function of the given optimization problem, and the best solution is the best value of the objective function. In TLBO, at each iteration, the mean of decision vectors is computed and denoted by M. The student with the best mark is designated as a teacher. Then, the position of all students is updated via the following equation 16, 18. 2. Learner phase. As in a real classroom, students learn from each other by discussions, presentations, and formal communications. In student phase, for each student I, another student J is randomly picked up, and then, the student with better mark, fitness, is attracted towards, learns from, the other student. That is if student J is fitter than student I, then. JAYA algorithm. The JAYA algorithm is a meta-heuristic which is capable of solving both constrained and unconstrained optimization problems. It is a population-based method which repeatedly modifies a population of individual solutions. 19. Initialize population size, number of design variables, and termination criterion. Identify best and worst solution in the population. Modify the solutions based on best and worst solutions. Is the modified solution is better than the previous solution? Accept and replace the previous solution. Keep the previous solution as the stopping criterion. Satisfied, report the optimal solution. Oye no. Proposed multi-population based modified JAYA, MPMJ, algorithm. In the proposed modified JAYA algorithm, an elite member in the population act as a guide to other members in the population to enhance their positions to a place near to the best known position. For the proposed modified JAYA algorithm, the mathematical equation can be shown in equation 18, below 20. Where L is a coefficient determined in each iteration as follows. If RAND 0.5 then L equals 1. Else L equals 1. And since the RAND value the number between 0 and 1. Figure 4, the algorithm steps for the multi-population algorithm can be explained. In the following figure 5, the application of the multi-population based modified JAYA, MPMJ, algorithm for the solution of optimal power flow without and with Statcom device. Start. Initialize the number of population design variable, maximum number of iteration, declare input data of transmission line, transformer tap setting, load and generator data, Statcom device data. Run the load flow using Newton-Raphson without and with Statcom device. Calculate the optimum power flow of the objective function with the initial population without and with Statcom device within the accept range of control variables, and save the value of the objective function for J equals 1. Identify the best and worst solution among the current population. Modify the candidate solution based on the best and worst solution. Run load flow for each modified solution, and calculate the value of the objective function without and with Statcom device based on the value of the objective function. Is the modified solution superior than the previous solution? Accept the new solution and reject the previous solution. Keep the previous solution. J equals J plus 1 is the stopping criterion. Satisfied. Display the optimal values. Stop. Generate an initial random population. Divide the population into subpopulation and apply flowchart on figure 4. Noise. 6. Result and discussion. The effectiveness of the meta-heuristic algorithm TLBO, JAYA, and proposed multi-population modified based JAYA, MPMJ, algorithm without, and with Statcom device are examined on standard IEEE 30, bus system to test the system for OPF problems. The optimal allocation of the Statcom device is selected by using the Analytical Hierarchy Process, AHP, method. The voltage, magnitude and phase angle of the Statcom device are 0.9 to 1.1 pu, and -10 to 10 degree, respectively. 21. The case studies for simulation are as follows under normal operating conditions. Case I, single objective optimization without Statcom device. Case 2, single objective optimization with Statcom device at the selected bus locations. Case I, single objective optimization without Statcom device. In this section, the proposed comparison techniques of optimal power flow solutions are evaluated using the IEEE 30 bus system. Figure 6, A, shows the convergence characteristics of the fuel cost of generation for the IEEE 30 bus test system under normal operating conditions without Statcom device. The minimum costs obtained using TLBO, JAYA, and proposed MPMJ algorithms are $798.79/HR, $797.8/HR, and $797.5/HR, respectively. Figure 6b shows the convergence characteristics of total real power loss for the IEEE 30 bus system under normal operating conditions. The minimum power losses obtained using TLBO, JAYA, and proposed MPMJ algorithms are 0.046 pu, 0.0288 pu and 0.0286 pu respectively. Figure 6c shows the convergence characteristics of the sum of voltage deviation for IEEE 30 bus system under normal operating conditions. The minimum sum of voltage deviation obtained using TLBO, JAYA, and proposed MPMJ algorithms are 0.203084 pu, 0.1133 pu and 0.0987 pu, respectively. Figure 6d shows the convergence characteristics of the voltage stability index for the IEEE 30 bus system under normal operating conditions. Figure 6d. Convergence characteristics of the sum of squared voltage stability index without Statcom device. Case 2, single objective optimization with Statcom device at the selected line locations. To get the optimal operation of the power system within the constraint, the selection of the best location of fax devices plays an essential role in the process of the power system. The considered locations of Statcom are the bus numbers 19, 24, 26, 29, and 30. These locations are taken based on the first 5 maximum voltage stability index of load buses from steady-state values of load buses. The value of the voltage stability index at bus 19, 24, 26, 29, and 30 is 0.0621, 0.0690, 0.0812, 0.0697, and 0.0822 respectively. The voltage stability index for load buses is shown in Figure 7. Table 1 gives the optimized values of different attributes at different alternatives. This OPF results with the Statcom device are used as a decision matrix for the system and then given as an input to the AHP method. In Pairwise Comparison Table 2, diagonal elements are taken as 1, which means objectives are of equal importance. The upper diagonal elements of the matrix have been taken by giving preferences to the attributes, and the lower diagonal elements of the matrix have been taken as a reciprocal of the upper diagonal elements of the matrix. Table 3 is a normalized principal eigenvector called a priority vector or weight matrix of the attributes. Since it is normalized, the sum of all attributes in the priority vector is 1, and the priority vector shows relative weights among the things that we compare. Figures 8a, 8d, show the convergence characteristic of each objective function with Statcom at bus 26 for IEEE 30 bus system, showing smooth convergence to the optimum value without spontaneous oscillations for best run under normal operating conditions. 7. Conclusion. The optimal power flow solution is the critical power system network resources, and various optimization strategies exist to solve the optimal power flow problems. In this paper, we applied the proposed MPMJ algorithm without and with Statcom device, compared to the recent literature algorithm results from the proposed algorithm method are contrasted with the recent literature in Table 5. From the result, it is clear that the proposed method can achieve better results concerning other algorithms for IEEE 30 bus test system. These values are not negligible because of the continuous operations of power dispatch throughout the years. The only parameters to be set for TLBO and JAYA algorithms are population size, several iterations, and number of runs. The only difference for proposed MPMJ algorithms is the number of initial subpopulation and modified original JAYA algorithm. The optimal values of the proposed MPMJ algorithm are converged early, including the Statcom device, and optimal values are obtained for the objective function of generation fuel cost, active power loss, minimizing voltage summation and enhancing voltage stability index. The proposed MPMJ algorithm is constructed using the exclusive collection of best group values and subpopulations. The key benefit of the proposed MPMJ algorithm to solve the OPF problem is that there is no tuning parameter and simple divergence control. Therefore, due to not using external settings, the result obtained is more desirable than the other meta-heuristic algorithm. Thus, the proposed MPMJ algorithm can be easily extended to solve the OPF problem with a quick convergence rate and the optimal result in the power system operating limits.